Hello, my name is Sierra Foster, and I am a junior chemistry and neuroscience major and biology minor. I'm from Davie County, North Carolina, and some fun facts about me are that I hope to become an optometrist and that I have two cats that I love to play with, socks and sandals. So for why I want to become a peer mentor is because I want to create the same relationship that I had with my peer mentors. I went every single week to a peer mentor session, and it really created a safe zone for me. I felt like I could ask questions that I thought maybe I didn't want to interrupt class, or I thought maybe were a little bit embarrassing. I can ask those questions easily and get them answered, and it was really nice. They really helped me succeed in all of my chemistry classes that I've had thus far, and they're really crucial into me doing well, and I really want to create that relationship with the students in the chemistry class. I want to be in that same role. For the upcoming semester, it'll be different because we're transitioning back to in-person classes. And I really hope to ease that transition difficulty by really influencing them to come to the afternoon peer mentor sessions. I know it's a walk across campus, but it'll be really worth it. I'll try to emphasize that. Also, I'll bring problem sets and work them out on the board in order to show them different types of problems and for them to see the problem-solving strategy. In addition, I'll also write up some directions to the location where the peer mentor sessions are. I remember getting lost in the labs as a freshman, and I think that is really important because not only are freshmen new to campus, but so are sophomores. So I think it'll ease some stress to have some nice directions to the location. And I hope that will be all, and let's get to problem solving.
Okay, so I'm quickly going to go over alkene hydration. So here we have our cyclohexane reacting with water and H2SO4. So our question is, how many products are there and what is the relationship? So here are the problem solving steps that I like to use, and we will use them as we continue. Step 1, evaluate the reactants. So what do we have? We have H2SO4 and water. So we know that H2SO4 is a strong acid, which means it completely dissociates. So here's our reaction. We know that this oxygen is the nucleophile because of the lone pairs, while this is the electrophile because the oxygen is pulling on the electron density. So remember, arrow is always nucleophile to electrophile. It attacks, and this hydrogen pops off, making the hydronium ion. Step 2, identify the electrophile. We know the electrophile will be in the hydronium ion, but what atom is it? Okay, so here we have to look at electronegativity. This oxygen is really strongly pulling on the electrons from the hydrogen because of its positive charge. So the hydrogens are extremely electron deficient. So that makes the hydrogens the electrophile. Please note, don't just blindly choose the atom with a positive charge. You need to look at electronegativities of the atoms surrounding it. Step 3, identify the nucleophile. Well, it's going to be the alkene, and it has electrons to donate. Step 4, draw the mechanism. So we know that you go from nucleophile to electrophile, and we know what those are. It attacks here. Okay, so now we're going to form a carbocation. What do we know about carbocations? They form on the most branched substituted area. So this area has 3, while this one only has 2. So the carbocation is going to form here, while the hydrogen bonds here, as seen here. Okay, so now we have new electrophiles and new nucleophiles. This is our electrophile. This lone pair on the water is your nucleophile. So now it attacks your carbocation because carbocations aren't very stable. Now, the water can add either from the front or the back, which brings up stereochemistry, which we'll get to. Also, here's water in our reaction because water is often solvent, so it's often in excess. So this water, the nucleophile, the free electrons, can come in and attack this electron-deficient hydrogen because the oxygen is pulling on it. So this hydrogen pops off. So now we have this product, this cyclohexane. Okay, so now let's talk about stereochemistry. This is an asymmetric center, but it stays the same. It's locked in. This is not where we're doing our reaction. Over here is where we're doing our reaction. So I said that water can add from the front or the back, meaning that there's 2 products on a wedge and on a dash. But these are asymmetric centers that stay the same. So there's two asymmetric centers, but one stays the same and one changes, meaning they're diastereomers rather than enantiomers. They're diastereomers because one stays the same. One of the asymmetric centers stays the same. Okay, so we have two products and they're diastereomers. And I just want to side note that this reaction is very similar if you have alcohol and you're adding it to an alkene.